Hi everybody, I'm Enge Song, coming from Alibaba Cloud. Now I'm going to introduce one of my research work titled Canal Mesh, a cloud-scale sidecar-free multi-tenant service mesh architecture. Microservice needs application network functions such as traffic management, security, observability, and so on. Traditional methods such as writing codes or using library in business logic has limitations. To this end, service mesh is proposed. The idea behind service mesh is decouple network functions from the application and move functions to a generic agent alongside the application. We call the agent sidecar, like the interesting figure show. Service mesh allows the application to remain focused on business logic, while the sidecar handles network tasks. After deploying ES2 on Alibaba Cloud for over 4 years, our production data indicates that such a proposed sidecar deployment causes the following problems. The first problem is high intrusiveness and the potential risks caused by embedding a sidecar into user pod. The sidecar and application coexisted, sharing memory, lifecycle, controller, and so on, which may cause potential security and stability issues. For example, memory leakage in the sidecar may cause the app to crash. Another problem is performance degradation due to extra steps, which is caused by traffic redirection to the sidecar. The traffic redirection introduces 2 extra steps of context switch, memory copy, and protocol stack processing, which degrade the throughput and latency by 3 times to 7 times. The third problem is sidecar consuming excessive resources initially allocated for user apps. Our production data reveals that when deploying KBS cluster with these 2, the sidecar consumes even thousands of CPU core and thousands of gigabyte memory, even larger than user apps in extreme case. Another problem is high control overhead of configuring too many sidecars. Since each pod has one sidecar and a cloud service could have hundreds or thousands of pods, the orchestration overhead is large. The configuring compilation time and the southbound bandwidth overhead are proportional to the cluster size. For cloud-scale service, the high control plane overhead could cause configuration delays or even losses. To address these problems, SIGCOMM' and Sprite use eBPF to reduce packet processing latency and CPU consumption. Despite their advantages, the eBPF-based solutions have limited programmability, making it challenging to support flexible Layer 7 processing, such as HTTP. Mint is a good solution. It decouples the complex L7 functions from the sidecar to an optional service-level shared L7 proxy, and deploy a per-node shared L4 proxy. Although Mint can somewhat alleviate the issue of proposed sidecar, there is still significant room for improvement. First, Mint wants to reduce the resource consumption and improve performance for users not using an L7 proxy by making it optional. But honestly, that design doesn't make much value. Based on our observation, the majority of our customers configure L7 rules in their service mesh. Second, the L4 and L7 proxy are still located in the same cluster of user apps, and in some cases, even on the same node. The incomplete decoupling still has potential risks. Third, Mint doesn't focus on performance improvement. There are still substantial room for performance improvement. Besides, since Mint's L7 proxy is shared across pods belonging to the same service, they experience synchronized peak and valley workloads, resulting in a reduced peak shaving effect. At last, Mint still requires configuring proxies proportional to the number of nodes and service, which still makes significant overhead to the control plane. Based on the above analysis, we have the following 4 design goals: non-intrusive service mesh, improve performance, less resource consumption, and control plane overhead mitigation. To achieve these goals, our first design principle is deploying the proxy outside the KBS cluster. Through fully decoupling, we can achieve non-intrusive service mesh. The remote proxy also can improve the performance by reducing the twice L7 processing to once. The second design principle is sharing proxy in service and tenant level. The tenant level sharing can achieve efficient peak shaving, then reduce the resource consumption. By consolidating per pod, node, service proxies, the number of proxies needed to be configured is reduced to 1, which mitigates control plane overhead significantly. Based on the above design principles, there is a stream architecture. All the proxies are consolidated into a cloud gateway, serving applications for all tenants. However, based on our experiences, such a stream architecture still faces numerous deployment issues. Since not all functions can be performed remotely without losing features, how to ensure function equivalence is the first issue. Second, the multi-tenant mesh gateway brings tenant isolation issues like virtual address overlap, failure isolation, resource contention, and so on. Third, the high capex of maintaining load balance for multiple gateway backends and supporting high concurrent flows is another issue. Then, we will show how we address the above issues of stream architecture. To ensure function equivalence, we follow the basic principle. Offload functions to the remote gateway as much as possible, except for those would negatively impact user experience if conducted remotely. Service mesh generally offers 3 major features: traffic control, zero trust network, and observability. We assess the remote deployability of 3 major service mesh features and show the results in the table. For traffic control, it includes route control, load balancing, A/B testing, and so on. Since the inputs can be carried by packets to the remote proxy, and the forwarding tables can also be configured remotely, traffic control can be fully offloaded to remote gateway. The Zero Trust Network includes encryption, authentication, and authorization. Due to distrust in the cloud provider's network, the data must be encrypted before leaving the user node and gateway, so the encryption cannot be fully offloaded. Because the certificate of each pod containing sensitive information for authentication, it is unsuitable for remote deployment. However, authorization is similar to traffic control, with input and processing logic being information carried by packets and configured rules, allowing for remote deployment. The observability of the service mesh includes metrics collection, logging, and tracing through instrumentation at critical points in the traffic path. The user experience of observability can be ensured by maintaining hooks both locally and remotely. Based on the above analysis, we deploy an on-node proxy to handle features that are unsuitable for remote offloading. Other features remain deployed remotely. To further reduce the resource consumption of on-node proxy, we offload compute-intensive asymmetric crypto to dedicated hardware, which is called key server. We report deployment issues of on-node proxy and key server in the paper. To ensure the high availability of the consolidated service mesh proxy, we configure each service across multiple AZ with multiple backends, each backend having multiple replicas. In this way, Canal can withstand sudden device or AZ failures and ensure that a service always has healthy backends available. To avoid packet header address space overlapping in multi-tenant cloud, we map VXLAN ID and the inner 5 table to a globally unique service ID and attach it to the inner header. Then, gateway can distinguish tenant service inside a virtual machine. While shuffle-sharding ensures a service always has healthy backends, traffic from failed backends can temporarily overload the healthy ones, potentially leading to failures. To this end, we propose 3 response mechanisms. First, scaling, which is used for handling normal case in gateway. We can scale in or out service backend list like this figure shows. Second, migration, which is used for handling anomaly case in gateway. We can update the list and migrate traffic to the newly added backends. Third, throttling, which is used for protecting users' KBS cluster. We may rate limiting users' traffic at gateway to prevent users' KBS cluster from being overloaded by hotspot. Next, we propose 4 anomaly detection mechanism. To ensure sufficient resource for user service, we monitor resource utilization and performance metrics. If any resources are about to be exhausted or the performance become worse, we automatically scale their resource to prevent user experience degradation. Besides, we will also check for service level anomalies and migrate the affected services to a sandbox. For the backend level alert, when a backend's water level over a threshold, for example CPU, an alert will also be triggered. Unlike at the service level, we first need to identify the root cause service causing the increased load, and then execute scale or migrate for this service. When traffic patterns among services sharing the same backend are similar, we scatter these services by migrating some service to other backend to prevent sudden CPU usage spikes. If the user's KBS cluster is hosted on our cloud, we monitor its resource usage in real time. If we see a sudden spike nearing 100%, we will discuss with the user whether rate limiting on the gateway to protect the cluster from being overloaded. The details and examples can be found in the paper. Each service has multiple backends and are different from other services due to shuffle sharding. Therefore, we need to maintain per-service load balancer for traffic redirection. To reduce the cost, we break down the functions of load balancer and conduct these functions on existing cloud info. That is, doing load distribution on the router and session maintenance on a redirector in replica. Such a cloud info reuse allows us to achieve function equivalence of traditional load balancers with almost no additional cost. In addition to load balancers, session also consumes substantial resources. After consolidation, our proxy needs to manage a large number of sessions. An imbalance between session and CPU usage is found. When the session is exhausted, the CPU utilization is only 20%. To address the resource usage imbalance of each replica, we propose session aggregation via tunneling. Then we will show the evaluation of Canal. Figure 1 shows the end-to-end latency of different solutions under light workloads. The latency of Canal is the closest to the no-service mesh baseline and is much lower than that of ES2 and Mint. Figure 2 shows the latency under changing workloads. The throughput of Canal is much higher than that of ES2 and Mint. This figure shows the CPU core usage under changing workloads. Canal consumes much less user CPU resources than ES2 and Mint. Figure 1 shows the compilation time for creating multiple pods. The configuration time of Canal is much lower than ES2 and Mint 2. As shown in Figure 2, Canal's sourcebound bandwidth occupation is much lower than ES2 and Mint because Canal only needs to configure one gateway. By aggregating sessions into tunnels after deploying redirectors, cloud resource saving can further reach 55% to 70%. We share our experience of deploying ES2 on Alibaba Cloud for 4 years and Canal for 1 year. For example, we observed that with the consolidated mesh gateway, health check probes significantly outnumber user app traffic. We reduce the health check with multi-level aggregation. The other experience can be found in the paper. At last, we make the conclusion. we propose the first cloud-based multi-tenant service mesh for production deployment. By deploying service mesh functions remotely in the public cloud, we address the issue of intrusion, performance, resource, and orchestration overhead of EC2 and Mint. Second, we present a production-valid system that addresses the issue due to remote deployment, service consolidation, and multi-tenancy. It achieves low cost, high availability, and elasticity. We share our experience of deploying EC2 on Alibaba Cloud for 4 years and Canal for 1 year. This ends my presentation. If you have more questions, you can email the first one, and if you want to try Canal Mesh, you can email the second one. Thank you very much.